this Chem Help video today, we're going to look at a basic titration calculation. Titrations are one of the most important calculations you can do as part of the Year 12 course, and they form a significant part of every WACE exam. This is the major type of calculation that we do in Year 12, so it's important that we get these right. We're manipulating concentration and volume. Hopefully prior to looking at this, you've had a look at the actual technique that involves with the titration, so you've understood how the burette works, how the pipette works, which indicators you choose and all that sort of stuff. So that's quite important. If you need some help with that, make sure you go back and have a look at that technique. But we're going to look at the actual calculation part, which is what you do post the actual technique itself. Okay, so for example, here's a typical titration question. It's got all the key points in there. What happens with these titration questions is they do have some significant key points, and to change them up, they change the chemicals around, they change the quantities, they sometimes put some distractor comments at the start, or you might introduce something called a back titration, so you can check our video out about that one as well. So here's our example. A 2.34 gram sample of an impure substance, so that's quite important, that word impure. So you can't calculate the moles of an impure substance, that's really super important. But we do know that that sample contains sodium hydroxide. The sample was dissolved in distilled water to make it into the free ions and made up to the 250 ml mark on a volumetric flask. So we precisely know the volume. But that's all we know about that solution, apart from the fact that it contains some sodium hydroxide. Now, it would be inefficient to test the whole sample and also inaccurate. We need to take lots of small tests. That's what a titration technique is. So we take a sample of that, 20 ml aliquots. An aliquot, remember, is what is dispensed from a pipette. We put that pipette sample into a conical flask and we titrate it. And 18.5 mils of a standardized 0.2 mol per litre hydrochloric acid solution was required to neutralize that sodium hydroxide that was in the impure sample. So what do we know about? We know the volume of the impure substance. We know the mass of the impure substance. But we do know precisely the concentration and the volume of the hydrochloric acid that came out of our pipette. And that's really important because if we know concentration and volume, we can figure out moles. In terms of our unknown substance, we know the volume in the volumetric flask. We also know the precise volume in the conical flask. That's what's called the aliquot. So the way these titration questions work essentially is this. We know what came out of the burette, concentration and volume. We can figure out moles. Whatever came out of the burette reacted with what was in the conical flask. So it's moles to moles. If we know moles in the conical flask and we know the volume, we can then work out the concentration and then we can flow on with the question. And ultimately this question wants to know about the percentage purity of the sample, and that's often important because if it's an impure substance, how much of our substance is actually in that original sample? So this is how you do the question. Calculate the number of moles of hydrogen ions, or hydronium, that reacted. That's what comes out of the burette. Then we figure out the number of moles of hydroxide in the aliquot, the 20 ml sample. That's the conical flask. Then we need to step it up from the conical flask to the volumetric flask, moles to moles, and then we can figure out the mass in the whole solution, and therefore we figure out the percentage purity. Here's a quick diagram to show you how that works. So first of all, here we've got our burette and our conical flask. The burette is the most important thing. It's a highly accurate piece of glassware. It can measure volumes to plus or minus 0.05 mils on a single measurement. Okay, so we dispense it dropwise from that until we get a precise change of indicator at what's called the endpoint, which we hope is as close to the equivalence point as possible. We've taken a impure sample in the 250 ml flask and we've taken a 20 ml sample of that via a pipette and put it into the 20 ml conical flask, or 250 ml conical flask here. So first of all, the one thing we do know about is what came out of that burette. We know concentration times volume. So the concentration was standardized, it's 0.2 moles per litre, and we know that it was exactly 18.50 mils. So it's 0.2 times 18.5 mils. And don't forget to convert it to litres. Often a really common error in these calculations is forgetting that we work in mils, but the standard unit is litres. And we get 3.7 times 10 to the negative 3 moles. So that's exactly the number of moles of hydrochloric acid that came out of that burette. Now, if we know our equation, and the equation is really important here, is that the number of moles of hydrochloric acid equals the number of moles of sodium hydroxide. So 1-to-1 ratio from that equation. So in that case, the number of moles of hydroxide in the sample is 1/1 times the number of moles of hydronium that came out from the hydrochloric acid. So we've got 3.7 times 10 to the minus 3 moles of sodium hydroxide in the conical flask, which is a small sample of the original. Now this is the kicker with these questions, and this is where people go wrong. We need to now step it up to the 250 ml flask, or the 500 ml, or the litre, depending on what the volume is. So you've got to read the question quite carefully. Step up is really important. So this is how we do it. All right. So we know that we can work out the concentration of the hydroxide is number of moles on volume. So we know the number of moles because we worked that out from previous step, and we know the volume because it came from the pipette, so it's really accurate. So we do number of moles over volume, so you can see that there, and we get 0.185 moles per litre. So that's the concentration of the solution in the conical flask. Now remember, when you take a sample from a big sample to a little sample, the thing that doesn't change is the concentration. Of course, the moles will be different because you're only taking a portion of the particles, and the volume is different, but the concentration is the same. So then what we can do is, if we know the concentration and we know the volume of the big solution, we take the concentration times the volume, and we get a number that should be bigger than the original number, which it is, which is 4.62 times 10 to the minus 2. So this 0.85 here, 1.85, that is the number of moles, the concentration in the aliquot, and this is the volume of the volumetric flask. A more efficient method is to look at the fact that the concentration equals the concentration. So we know that. And if we sub in that concentration is number of moles on volume before, it must equal number of moles of volume afterwards. So then we have this really efficient calculation here. When we step up, the number of moles of sodium hydroxide in a big sample is always the bigger number, that's V2, over V1, the smaller number, times the original number of moles. So you can manipulate these however you like. So if it was 500 over 25 or 1 litre over 15, whatever it might be, it's always got to be the big number over the small one, and we step it up from the original to the next size flask. All right, so you can do it that way. So there's two ways. You can take the moles, work out the concentration, take the concentration and the volume, work out the moles. Or you can combine it in one step, acknowledging that concentration is equivalent. Once we've got the number of moles in the big sample, it's simply a matter then of calculating what's the mass of that. So we say, all right, in this case, there's 1 hydroxide per sodium hydroxide, so it's a 1-to-1. And therefore the mass of sodium hydroxide is the moles times the molecular mass, and we get 1.85 grams. Now that number has to be smaller than the impure sample. If it's bigger, you've made a mistake somewhere. So we've got our mass, and that's pure sodium hydroxide. And step 6 is where we look at the percentage purity. All right, so that's where we take the mass of the pure over the mass of the original impure sample and times it by 100, and we get 79.2%. So that's a basic titration question. They always follow the same basic steps. Burette first. Conical flask, second. Volumetric flask, third. Mass, percentage. So they follow, those basic questions follow that same pathway. So hopefully that's made the understanding of a titration question a little simpler for you. The key to these is practice. You've just got to try and try and try lots of different waste questions, because a lot of the time it's not the process, it's the packing, it's the words they put around it that can be confusing. All right. There's also another concept called a back titration. There's a separate video on that. Hopefully, if you look at that one, that'll make a bit more sense to you. So give that a go too. But that should give you some background. Okay? Good luck.